Welcome. This is Mass Expert Video Tutorials, and here we are. Further statistics. So in this course, you are going to learn something about randomized complete design. We also have randomized block design, and we also have Latin square, Greco-Latin square, factorial design, and all that. Trust me, you will love it. Alright, so we are starting from completely randomized design. So when we talk, or when we say that, when we talk of a completely randomized design, what are we saying? Alright, so when we talk of completely randomized design, we are saying it is a single factor design. So in this design, we can see that it's a single factor design. Treatments are assigned completely at random, so that each experimental unit has the same chance of keeping any one treatment. What we are saying is that in this design, we assign. That's a keyword. We assign. We assign what? So treatments are being assigned. So there is another word here to take note. We have a treatment and we have the experimental unit. As treatment and experimental unit. So in this type of design, the treatments are being assigned completely at random, so that each experimental unit has the same chance of keeping any one treatment. For instance, let's say that we have cookies or pie or bread to share to let's say a bank. Now we are going to check the number or the population in the bank, so that if we are going in with the pie, we go in with the same number, so that it will not be a case that somebody will be there and he will not going to get his or her share. So we are saying that it's a single factor design. So treatments are assigned completely at random. So it's going to give it's going to be given to them randomly, and each experimental unit have the chance of keeping any one treatment. All right. So let's see the assumption. The first assumption is that a normal population has a common variance. A normal population has a common variance. When we talk of the common variance, we are talking of equal variance. Alright. 2. A population at its factor level is approximately normal. A population at its factor level is approximately normal. 3. The observations are obtained independently. The observations are obtained independently. It's not going to be dependent. It's not going to be the case that you are going to share the cookies or the pie. That there will be a case that it's going to be something like 2 for 1. No, it's not going to be something like 2 for 1. Each experimental unit will receive his share, the same chance of keeping any one of the treatment. Alright. So randomly from population defined by the factor level. Alright, so now let's go through how we can solve a question under this. Now, under the RCD, which is completely randomized design, we have the case that we deal with equal sample and unequal sample. So we are going to see how we are going to come out with a solution for these two samples. Alright, see you. Alright, so welcome to our first question under the CRD. So this person saying that a study is undertaken to determine the relative performance of agents of 4 competing real estate companies. So it means that we have how many companies? 4. Alright. The companies are the treatment. So here we are using the companies as what? The treatment. Alright. Are the treatment. Random sample of 5 agents are selected. So how many agents were selected? 5. Alright, so those 5 are what we are going to use as our random sample. From each company and the number of homes sold by each agent in a 3-month period is recorded below. So we have the 4 companies here, and then we have the 5 agents here. So these are what? The recording. So what are we asked to do? I'll be back with it. Alright, so we are using a significant level of 0.05. That means that the upper level is given to us as 0.015. Determine whether any difference exists between the process of allocating the total sum of the squares and degree of what? The freedom. So let's see how we are going to go about it. Alright, so the first thing to do is to state our what? Hypothesis. So the hypothesis is that you state the what? The null hypothesis, then you state the what? The hypothesis. That's where we consider the number of companies. So how many number of companies do we have? 4. So that is mu1, mu2, mu3, mu4. Then that's that. So you know that our sample is the number of agents, that is 5. So that is then the company represents the K. So that is that. Alright. So you multiply the n by the K, then you get what? 20. So since from what we are going to find, we will need t squared. Then we have to sum all the what? The t's. The t's here is the total of the whole of this. The total, so the total of all this is T1. The total from here to here is T2. The total from here to here is T3. That's what is here. Total from here to here is T4. Is T4. And all total gives what? 304. So 304 squared is what is going to give you what? The T squared. Alright, so from there, then we go to sum of square what? Total. This SST means sum of square what? Total. So the sum of square total, that is when, now, this is the formula we use to find the sum of square what? Total. The I you see here is the row. That is why it's representing the n here. You see, that means that we are summing all the what? The rows and all the what? The I is the row. So the I is the row and the J2 represent what? The ones here. Alright, so we have the row and the what? All of it. Alright, so now from here let me go and find our what? Sum of square what? Column. So the sum of square column, the formula used to find the sum of square column is what? This. So now, the summation of t square j here is what you have to understand. So this one means that we are going to sum all the totals of what? T's. The t's there, we are going to sum all of them, but in summing all of them, you have to square each. It's not add them before you square. It's square each of it before you what? You add. Then you divide by what? The n. Minus the t square over what? The n, the nk. Alright, and you know the nk is 20. So that's what we are going to have there. And doing that will give you this. Alright, so always don't forget this. The I is a row. and the J is the right. Alright. So now, after getting the sum of square column, which is this, then we use that in order to get the sum of square what? Error. Because we have already found the sum of square what? Total. And always the sum of square total should be greater than the sum of square what? Sorry? Always the sum of square total should be greater than the sum of square what? Yeah. So that's that. Because it can be a case that when you subtract, you get a negative value. If you get a negative value, it means that something is wrong. Alright. So when you subtract this from this, you are going to get this. So from here, we are going to see how we are going to calculate our F words calculated. Oh, okay. So now, let's come. So we are done with that. We have sum of square total now, sum of square error, and sum of square C. Alright, so let's come to the mean square C. The mean square C. So now, the mean square C means that SAC over what? K minus what? 1. So we know the sum of square C to be this. This is 4, that gives you that, and computing gives you this. And that 1, 2 is like this. And you go your way. Alright. So what we have here is the degree of what? Freedom. Is the degree of what? Freedom. Don't forget that. Alright, so now let's see how we are going to calculate for. So from here, our F calculated is going to be, that is the F calc. So the F calculated is going to be the mean square column. The mean square column over the mean square error. So the mean square column over the what? The mean square what? Error. And we know that to be 96.13 over 13.925. And the results of this will give you 6.903. So, alright, so after getting this, that becomes your test what? Statistic. That becomes your test statistic. So now, from the 4-figure table, under the F table, at where we know that we are using the alpha level of what? We are using the alpha level of 0.05. It's so unfortunate that I don't have my F distribution table here. But I hope you have your own. So this is what you do. You open to that page, think 49 or so, or 50. Then you check where you get 0.05. Alright? So you're going to check where you get 0.05. Then you compare it to it what? And you compare it to the degree of what? The freedoms. So this is how it's going to be. Alright, so now, the alpha, K minus 1, and that. Alright, so from here, we know that our alpha is 0.05 given in the question. This one is this, which is 3. Yeah, that is K minus 1, 3. And we know this one to be 16. So what I'm going to do is that first, check where the table of 0.05 is giving you. Then, you check on 3. You trace the 3 to the 16. The 16 are the ones here, and the 3 are the ones here. So, when you trace, you are going to get that to be 3 points. You are going to get that to be 3.24. 3.24. So that's going to be your F distribution value for that. Alright, so now, after here, we are now going to state our decision. The decision. So what's going to be your decision? Don't forget each step. So we come to the decision. And the decision, alright, so the decision. So you can see that F calculated, check the value. You see that is greater than what? The F alpha. Is that also? So the F calculated is greater than what? The F alpha. That means that we will what? Reject the what? The null hypothesis. So this means we reject the H naught. We reject the H naught. And if I'm giving you in general, if F calculated is greater than the F alpha, that means that we reject the what? The H naught. We will come back to the question. And if F calculated is less than F alpha, that means that we will fail to what? Reject. So this means that we will fail to reject. We will fail to reject the what? The null hypothesis. Alright, so now looking at this decision condition, where will this question fall? The F calculated is 8.9, the F alpha is 3.24. So you can see that the F calculated is greater than the F alpha. So therefore, we will reject the what? The null hypothesis. So we reject the null hypothesis, and this is going to be the graph. And this is going to be the graph. That is the normal distribution. Okay. Alright, so we are going to have our 3.24. Then let's say our 6.903 is here. Alright, so you can see that since we are F calculated is greater than what? The F alpha, we say we reject the null hypothesis. So when we reject it, it means that we shade this part. Alright, so what is going to be your conclusion? Okay, so right. So since the F calculated is greater than the F alpha, we conclude that at least there is a means that, so it means that at least the means are not equal. This means the mean number of homes sold by agents during the 3 months is not the same for the 4 what? Alright, so that's going to be your conclusion. The 4 RE, that's the rate what? Agents. Alright, so that's it. Now, after being done with everything, then you go and draw your what? Your ANOVA table. So we are now going to draw our what? Our ANOVA table. Alright, so after that, here we are. So you come to your ANOVA what? Table. So that's where you're going to present your results. So this is going to be the ANOVA table for any equal what? Sample. Alright, so you have the column, the error, and the what? The total. You have the SS here, sum of square column, sum of square error, sum of square total, and all that. And each degree of freedom. You know this degree of freedom is a k minus 1. And this degree of freedom is, that one is the what? Alright. And this degree of freedom is a k n minus 1. table because sometimes you can be given some part and the other part will not be given to you. Now you can be testing something and see. You can be testing something and see that if you multiply this by this, you are going to get this. You try it and see. Three times 26.13. You see, when you multiply this by this, you get this. You multiply this by this, you get this. And the reason is from where the formula is what coming from. Because you know that sum of square, let's say column, is equal to what? The mean square column over 8 what? Degree of what? Freedom. So it means if you multiply this by this, you come back to this. Alright, see you for the next video.